Alright gang, here we go. This is for Chem 2 Unit 9. We're going to be talking about first, second, and zero order reaction kinetics and talking about their integrated rate laws. Yes, that's right, I said integrated. We're going to use some calculus today. That's pretty exciting. Alright, so just to recap a little bit what we've talked about in the previous video, we talked about how we could take experimental data and run different experiments and be able to determine what the reaction order of a reaction is, both for the overall reaction and in regards to the individual reactants that are in there. Alright, and so we're going to talk about another thing that is unique about, specifically we're just going to focus on these three different types: first order reactions, second order, and zero order reactions. Alright. And we're going to talk about some unique properties and formulas that we can derive from their unique some their properties and kind of how their reactions and their equations kind of work out together. All right. So if we have a first order reaction, this is a reaction that depends only upon the concentration of one thing. All right. So there's lots of different ones of these, and we've looked at a couple of these in our previous videos. But in general, their rate law looks something like this: the rate of the reaction is equal to their K value times the concentration of one reactant. All right. And so the conversion of methyl isonitrile into acetonitrile is a first order reaction. All right. So essentially, all that's going on is this nitrogen and carbon are flipping places, and so this just takes a little bit of energy to get it started. And I believe acetonitrile is at a lower energy level than the methyl isonitrile. Anyway, but it's a first order reaction regardless. Okay, so here in this slide we're just doing some fancy algebra mumbo jumbo. Okay, and you'll notice that in this video there's going to be a couple of times where we're just briefly going through the algebra of how to derive these things. Okay. So we know from the rate law that the rate is equal to this guy, K times the concentration of A, and we know from several videos ago that that we can relate the concentration of A to the rate by dividing by the change of time. All right, and because it's a reactant, we'll have to throw in that negative value. All right, so we're going to take both of these two guys here and make them equal to each other. Because they're both equal to the rate, we can set them equal to each other. All right, so the Ka is equal to the negative the K times the concentration of A is equal to the negative concentration of A divided by the change of time. All right, and we can rearrange this to get K and T on one side, and it comes out looking like this. And if you've taken calculus, you should know that if we take the integral of this, and the integral is kind of like taking the antiderivative, which is like taking the derivative backwards. All right, so anyway, so the integral, but we're doing it over a specific amount of time. Okay, that's our delta t, and if we take the integral of this, we end up with this guy here. All right, the natural log of the concentration of A over the concentration of A naught, so this is our initial concentration, is equal to negative kT. So this is the concentration at whatever time we're talking about, and then this is the concentration of A that we started with. Okay, now using some, remember, if we have this over this, this would become the natural log of the concentration of A minus the natural log of the concentration of A naught. These two things are the same thing, right? This side of the equation and this. So we can take that and solve just for the concentration of A, and we end up with this guy. So this here is known as the integrated rate law for a first order reaction. Okay, integrated rate law for the first order reaction. If you look at it, kind of squint your eyes and stuff, you'll notice that it looks very much like this equation, right? Y equals mx plus b, which is the standard slope intercept form of a line. Okay, so your y value is your natural log of your A. Okay, your k value is, or your slope, your m, is your negative kt. Your x is your t, and your y-intercept is this natural log A naught. And if we take these values, okay, for whatever, if it's a first order reaction, and we plot them, the natural log of A versus time is a linear line. It's pretty wild. Okay, so we'll do the same thing with this conversion of this isonitrile into acetonitrile. Okay, and we can see that if we plot so they're doing pressures, but because pressure and concentration are proportional to one another, we can use pressure instead of concentration. It's no big deal. So they're plotting the pressure versus time, and we get this graph here, and then they took the natural log of each of these values and graphed it versus time, and notice that we get this linear line here. And so the slope of this line would be equal to, the slope would be equal to our negative k value. So based on just, if we can, so before we were able to find the k value and the reaction order by taking the reaction or by looking at several different reactions in a row, right? Where in each one we're changing the reaction or the concentration of one of our reactants. Then here we can take we can just do one reaction, okay? And if we can take the concentration as it's changing as our guy goes, as our reaction progresses, we can find the reaction order and then also the K value just from that, okay? So we can use this. This is essentially what we just said. If we take the slope, that slope would be equal to the negative K value. All right. Okay. We can also find the half-life. All right. So here's a little bit more derivation. Okay. Remember, so I'm not sure if we've talked about half-life before, but here's the definition of half-life. Okay. You've probably learned it in other classes. The definition: the amount of time it takes for 1/2 of a reactant to be used up in a chemical reaction. So if you start at 100 grams and in 10 seconds you have 50 grams, that means you had half of it used up, and so that way your half-life would be the 10 seconds. Okay. If another 10 seconds go by, you'd have 25 seconds, and then or 25 grams, excuse me, and then 12.5 grams after another 10 seconds, and then et cetera, et cetera. Okay, so half-life by definition is that you have half of your initial starting. So here's our integrated rate law that we just established. We just derived this. And then simply at the half-life, we know that the concentration of A should equal half of whatever our initial concentration was. So we replace that with concentration of A naught divided by 2. And the T becomes T1/2 for half-life, all right? And then we rearrange this to solve for T1/2, and then some more mumbo jumbo, and then we get this guy right here, okay? That the half-life of any first-order reaction is equal to 0.693 divided by K. All right, so we can find our value just by taking, we can find the half-life of anything that's first order just by as long as we have that K value. You just take the natural log of 2 divided by K, or 0.693 divided by K. All right. Second order reactions look something like this. Rate equals K times the concentration of A squared. Okay. All right. Now this is specific to when it reacts with only one reactant. Okay. If there's two reactants, if it's like A times B, then that becomes a little bit more complicated. All right. But it follows the same general rules. Okay, but we can't make quite the same broad assumptions. All right, but we're just going to go with the second order reaction. Rate law looks something like this. Plug them, set them equal to each other, the K squared and this guy, and solve, and then we get this guy right here. And there's our integrated rate law. All right, so write that guy down. That guy's important. All right, so notice that linear relationship, right? We still have that y equals mx plus b. Right, our y value would be the inverse concentration, and the mx value, well, they flipped it on us. So, but the m value would be our k, and our x value would be our t, and then the y-intercept is the initial concentration of A naught. Okay, and so we can graph these guys as well. So this is decomposition of NO2 is also a second order reaction. This is the equation. And notice that if we graph what we started with before, for first orders was the natural log, we have a curvy line here. Look at that curviness. And then for the inverse nitrogen dioxide, we get this straight line. And we know that the slope of this line would be equal to our K value, because that's what it says in our mx plus b. All right, we can also find the half-life of a second order reaction. Okay, that's pretty easy. All right, once again, we take our A and turn it into A naught over 2 and then solve for T1/2. All right, and eventually we get this guy. Okay, right there. So the half-life is a concentration-dependent quality for second order reactions, which is a little different than the first order reactions. In first order reactions, it didn't matter how much we started with. Okay, in second order reactions, it does. Our half-life changes depending on the concentration. Pretty bizarre. Okay, the last one here is zero order reactions. Right? These are reactions where the rate is independent of any concentration. It doesn't matter how your concentration is, your rate doesn't change. Okay, so in this case, in a zero order reaction, and these are fairly rare, our rate equals K, just straight up. Okay, and so these are zero order reactions, and these are, instead of deriving it, okay, and we're just going to set it equal to this guy here. All right, this is our integrated rate law for a zero order reaction, and they've went ahead and graphed it for us here. Just they got, I guess, the PowerPoint makers got lazy, and you can see that the concentration of A versus time, all right, is linear for a zero order reaction, but it's curvy for a first order reaction, and it's also curvy for a second order, but they don't show it here. All right, so the integrated rate law allows us to graph these guys versus time, okay, in order to determine what order of reaction we have. All right. Okay, so you can start with any reaction. We'll do this in the lab. We'll start with reaction and be able to use absorbance to calculate, the concentration and as it changes over time. And then we can graph these guys versus time, the concentration of A versus time, natural log of A versus time, and the inverse of the concentration over versus time. And depending on which one is linear, okay, we can tell if it's a zero, a first, or a second order reaction. All right, and so then from there you can tell, well, which of these integrated laws, half-life, and so on and so forth can we use. All right, so these are just generally here to help you identify what's going on. So notice that in a zero-order reaction, our concentration versus time is linear, and our slope equals negative, or k equals negative slope. All right, and notice that the natural log of A is curvy and the inverse is curvy the other way. For a first-order reaction, okay, the concentration is curvy, but the natural log is straight, and our k equals our negative slope. All right, and then finally for a second order reaction, this is the one where where the positive slope, our k is not negative in our equation, so therefore our k equals our slope straight up. All right, so let's do a couple practice problems here. All right, it says at 25 degrees Celsius, the decomposition of nitrogen N2O5 into NO2 and O2 follows first order kinetics with K equals 3.4 times 10 to the minus 5th seconds per second. A sample of N2O5 with the initial pressure of 760 torr decomposes at 25 degrees until its partial pressure is 650 torr. How much time in seconds has elapsed? All right, so that says it's first order. So first order means this is the natural log jobber. So that we'll say the natural log of A is equal to negative KT time plus the natural log of A naught. Okay, and it says how much time in seconds has elapsed. So we're going to solve for t. So we're going to subtract this over and divide by negative k. So our time is equal to natural log of concentration of A minus natural log of concentration of A naught. All right, over negative k. All right, and remember we talked about earlier how pressure and concentration are proportional to one another, so we can just plug it in without regards to changing it to concentration. So that means the natural log and our concentration, the second concentration was 650 torr, so we'll just say 650 minus the natural log of the initial concentration. Well, that's the 760 there. All right, divided by our negative k, and it gives us our k, which is 3.4 times 10 to the minus 5th. Now notice that the k has units of per seconds, and it wants it in seconds, so we don't have to worry about converting it. All right, so our t value here, so we'll take the natural log of 650 minus the natural log of 760 divided by negative 3.4 e to the negative 5th. All right, and we want how many sig figs? It looks like 2 sig figs, so 4598 rounds to 4600, and it's in seconds. 4600 seconds. So our answer is right there. All right. Okay. Let's see. Let's do this one too. All right. It says the decomposition of here. If you need to look at that, you'll just have to rewind the video. Sorry. All right. So it says the decomposition of dimethyl ether. Okay, at 510 is a first order process. Well, that's nice because we already have that one written out. With a rate constant of this, there's our rate constant. All right. There's a reaction. If the initial pressure is 134, what is its pressure after 1420 seconds? All right, so we're looking for the pressure after a certain amount of time goes by. So we don't even have to rearrange it. We just got to move our natural log over. So our concentration of A would be equal to E to the negative KT plus natural log of concentration of A naught. All right, so now we just plug things in. So E to the, all right, negative K value, which is 6.8 times 10 to the minus 4th, times our T, which is 1420, all right, plus the natural log of our initial concentration, which is 135. All right, so the concentration of A is equal to, all Where is it in this calculator? All right. E to the negative 6.8 to the negative 4th times 1420 minus, or plus the natural log of 135. All right, and I got 51.4. How many sig figs? 2 sig figs, so just 51. So the concentration after 1,420 seconds is 51, and it would be in torr because our original was in torr. All right. Okay. So on this guy here, it says the following data were obtained from the gas phase decomposition of nitrogen dioxide. This is a reaction first or second order. So we're just going to watch we're going to develop our own idea, and then we're going to see if they do the same thing. Okay, so we've got this time here, all right, and we've got the concentration of NO2, and it's a first or second order. So what we want to do is we're simply just going to graph this, and what we want to do is we're going to figure out the natural log, figure out the values of the natural log of NO2, right, and then figure out the inverse of all these as well. NO2. Why? Why are you doing that to me? Okay, and then if we can graph all those, all right, and then one of them should be linear, right? So I think they're going to do the same thing. Sure enough, they say we can plot natural log of NO2 and inverse of NO2 against time. If one plot or the other is linear, we will know the reaction is either first or second order. So there they go. There's the natural log and the inverse. All right, take those guys there and then plot them. Sure enough, it's linear with regards to the inverse. All right, so therefore it is second order. All right. Let's see. All right, let's do one more here. The decomposition of NO2 in sample exercise is the second order. Okay, with respect to that, if the initial concentration of NO2 is in a closed vessel, is this, what is the concentration of this reactant after 0.5 hours? All right, so this one's kind of tricky. Okay, because it's second order, so the thing for second order was 1 over concentration equals KT plus 1 over the initial concentration. Right? It's positive KT. Pretty sure. Pretty sure. Maybe we should double check before I look like a fool. That's the half-life. Yeah, positive KT. See, I told you. I told you. I told you. I told you. All right. Bow, 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 bow. So much stuff. All right, here we go. And then it says, what is it? This is, if the initial concentration is this, what is the concentration of this reactant after 0.5 hours? Okay, so we're solving for this guy here, but we got to flip it over. So we'll say the concentration of A is equal to all of this inversed, and that's, we're just going to put that like this, so it's everything to the -1. All right, so our K value, we'll notice here that our K value is in per seconds, and this is in hours, so we're going to have to convert this to seconds. All right, so 0.5 hours, so that'd be for every 0.5, so for every hour there's 60 minutes, and for every minute there's 60 seconds, so that's 1,800 seconds. All right, 1,800 seconds. Okay, so K value is 0.543, and the time is 1,800. And plus 1 over the initial concentration, 0.05. All right. So 0.543 times our answer from the previous one, which was the 1,800 plus 0.05. Inverse, and then inverse the whole thing. So the concentration after 1,800 seconds is 0.00100. Man, just not very much, is there? So 1.00 times 10 to the -3rd molar. All right, I'm pretty sure that's all I wanted to do. Actually, let's do this. Practice exercise 1. Okay, this one is a half-life problem. All right, so it says So we noted in an earlier practice exercise that 25 degrees Celsius blah 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 follows first order kinetics. All right, first order kinetics. Okay, so that means we've got natural log of the concentration. I'm just writing down my stuff now because I'm not quite sure what I'm going to need, but it's always nice to have everything written out. Okay, and then the half-life, and I know it's a half-life because it says half-life right there, is equal to 0.693 over K. Right, 0.693, natural log of 2. Nailed it. All right. How long will it take for the sample originally containing 2 atmospheres of N2O5 to reach a partial pressure of 380 torr? Oh, those little devils. We need to convert our torr to atmospheres. Okay, so we'll do this real quick. So we'll set up our thing. We'll put torr in the bottom. Put why do you do this? And atmospheres in the top. All right, for 1 atmosphere, we have 760 torr. So we'll take our 380 divided by 760. So we get half a torr, or half an atmosphere. All right. So what we need to do is we need to solve for the half-life of this guy here. Okay, so how many half-lives? Because it says how long will it take for this sample to go away. We don't really have. What we could do, so let's do it this way. So we have the K value, so we can figure out what the half-life is. So the half-life of our equation, 0.693 of our reaction, would be that over our K value, and they give us that, so that would be the 3.4 times 10 to the minus fifth. All right, so we have 0.693 divided by 3.4 e to the minus fifth. All right, so that's 20,382. All right, 20,382. All right, so the seconds, that's the half-life of our guy. Now to go from, oh, I didn't write down point equals 0.5 atmospheres. All right. Okay, so to go from 2 atmospheres to 0.5, we'd have to go through 2 half-lives, right? So we go from 2 to 1. That would be 1 half-life, and then we go from 1 to 0.5, so that'd be 2 half-lives. Okay, so we know that we should have 2 of those guys go by. So, and then we also see that they're giving them to us in hours, so not seconds. So we need 2 of our half-lives, so that'd be 20,382. Okay, and then we also, and this would be in seconds, and we need to convert this to hours. So for every 1 hour, we have 3,600 seconds, right? 60 times 60. Right, seconds. All right, so we take 2 times our answer from the previous one, divided by 3,600, and we get 11.3, but everything has 2 sig figs, so it'd be 11 hours. 11 hours. All right, so C again. Imagine that. Okay. And that's all we're going to do for today. Do your practice problems. Let me know if you have any questions. The stuff that can be kind of tricky, so just stick with it. Don't worry so much about the derivations. It's important, but it's more important to be able to apply these integrated rate laws, so on and so forth. All right, so let me know if you have any questions, and I'll see you on the flip side.